you can start working on them three. Okay. We quickly went through how to implement Semaphore, but today let's go through its implementation line by line. So it's I think for me it was interesting to move from using Semaphore to learn how to implement Semaphore myself, right, when I was taking OS course. So hopefully this difference, right, between using some mechanism and implementing such mechanism yourself. Hopefully this is also interesting to students. Okay. All right. So, all right, we're getting started. So let's start with where is Semaphore stored. Right, so we explained this. Where are these semaphores stored? And what are the data members of a semaphore? And where are these data members? Where are they stored? And where are they pointed to if they are pointed? Right? Anyone can try to give an explanation. Right? It's all there on the slide, right? So, but if you can explain, that would be helpful. I'll give everyone like 15 seconds or so. Right? So think about this. It's the same as when you are learning data structures and algorithms. You first, for any problem that you are designing a solution for, you first need to know the data structure. Once you know the data structure, then after that you can start implementing your algorithm. So what are the data structure for Semaphore? Where are they stored in Linux? Sorry. Someone raise their hand first. Go ahead.
I was going to say it's probably some global variable handled by the operating system that either when we have like the rescheduler or like during reset or some other interrupt, we want to handle it to see, like, to keep track of the process queue and to pick a new process whenever we have updated the semaphore entry. But I guess it could also apply to just any parent process that handles multiple child processes that would use a semaphore.
The idea is definitely there. The idea is correct. Understanding is correct. But mapping to the concrete implementation. Right? So there is a global structure that stores all the semaphores. It's similar to the global structure that stores all the processes. Right? The global structure that stores all the processes are process table. And the global data structure that stores semaphores are this semaphore table, SemTab. Okay? And similar to process table, top tab, every item in semaphore table is a semaphore entry. Right? SE. And in this S entry, you have a state which is much simpler than process state. In process, you have many different states, whether it's current, whether it's ready, whether it's waiting, whether it's suspended. Process has many different states. But Semaphore only has two states, whether it is free, whether it is being used, free or used. Sorry. Sorry about that. State is simple. The second data member, this scont, what is it? What is this data member? What is it used for? The third one, I think the previous student explained it. The third one is a queue. The second one, scont, what is it? Yes. Right, exactly. the number you use to initialize the semaphore, right? And for example, you initialize to be 1, then when one process calls wait, the next it will decrement it, and the next process will block on the semaphore. Okay. So that is the number that you use to initialize the semaphore. And the next one, SQ, that is the queue or the list that you use to keep track of all the processes that are blocking on this specific semaphore. Right. So there will be multiple processes using this semaphore. Some of them will be able to use it, some of them will be blocked. And these processes that are blocked on the semaphore, they will put themselves into this queue. Okay. What is the reason? So the reason is that in the future, when the other processes finish using this semaphore, they will call signal. Right? If in 252 you know that when you use a semaphore, you call wait. When you finish using it, you call signal. When such a process finish using the semaphore, when they call signal, it will wake up the processes that are waiting in this semaphore queue. Okay, so it will wake up the semaphore queue in Zimu is first in, first out. So it will wake up the first process in the semaphore queue. That is the purpose of semaphore queue. It keeps track of all the processes that are blocked on this specific semaphore. Okay. All right. And we went through the implementation of wait and signal very quickly, but let's go through it slowly this time. Wait, when you use a semaphore, the first thing that you do is you call wait. Right? When you call wait, forget about these lines for now. The important thing is here. This is the core logic of wait function. Right? You do it. What you're doing here is very simple. Right? You are going to decrement this number, and if it's smaller than 0, it means that you need to be blocked. Right? This process needs to be blocked. And if it needs to be blocked, you'll get its process entry. Change its state to wait, right, meaning that it's blocked, and set its semaphore pointer to this the current semaphore being used, and in queue this process to the semaphore's queue. Right, so this process will be put into the semaphore's queue. Okay. So that's how the blocking, the process being blocked is added to the semaphore's queue, and then you call rescale, right? Which means that the current process is blocked, so let's switch in another process. Okay. So in the future, we also explain this briefly, right? So in the future, when will this process be switched in again? Yeah, the current process calls wait and got blocked on this semaphore, and called rescale, which means that the current process is switched out. Okay. When is this process going to be switched in? There will be another process who was using the semaphore and call signal. When they call signal, that process is going to release this semaphore, and it also signals the processes that are blocked on the semaphore. And if this current process happens to be the first one in the semaphore queue, it will schedule it back. It will switch back to this current process. Okay. Any question about wait? there are really two functions that are critical for semaphores implementation, wait and signal. This is the core logic of wait. Yeah, so the current queue in semaphore is first in, first out. Okay. We'll come back to this later. Okay, so the semaphore queues, the decision of semaphore queue is actually quite tricky. Yeah, here. Signal, right? So the implementation of signal. When the process finishes using a semaphore, it will call signal. So this signal, the purpose of it is that it should tell the other processes I finished using the semaphore, and one of the process will be woken up. Okay, so what it does is it here gets the semaphore from the semaphore tab and increments semaphore's count, right? And call DQ and ready. Can anyone try to explain what exactly is happening here in these two functions? Yes.
You remove a process from the semaphore's queue and mark it as ready.
But what exactly happens inside this? That's a function name, but inside DQ and ready. I think more importantly ready, right? So DQ is straightforward, and the only subtlety here is that DQ it removes the first item from the queue, right? It's the first in first out queue. But ready has some has more subtleties inside. What does ready do inside it? Yes.
It also calls rescan.
Right. Ready calls rescan. Ready first inserts the item back into the ready queue, and then call rescan. And these two things are very important. Okay. So that's how it wakes up a blocked process. Okay? If you don't put the blocked process back to the ready queue, and you do not call rescan, that process will never be waken up. Okay. Right. So ready. So DQ removes one blocked process from the semaphore's queue, and ready will add this previously blocked process back into the ready queue, and then rescan will probably, so in the future, maybe, depending on the priority of the process, will switch in the previously blocked process. Okay. All right. So this is a signal, right? So hopefully, right after looking at these two functions, you will see that implementing semaphore is not that complicated. Right? So previously in 252, I guess everyone has been using semaphore, but implementing a semaphore inside the OS, it looks like this. This should probably be the simplest implementation of a semaphore. Okay. All right. So the many of the implementation detail are very straightforward. It's really list manipulation. The subtlety or the trickiness is these ready, right, where you do context switch. This is if you ignore context switch, then the entire implementation of semaphore is just removing from a list, adding back to a list, and that's about it. Right? Adding to a semaphore queue, remove from a semaphore queue and put it back to the ready queue, and that's it. Very simple. The subtle the subtlety of semaphores implementation is in the context switch, and context switch has already been designed and verified solidly in our previous discussion. So the point is that if your OS is designed cleanly, like providing a very clean context switch functionality, implementing semaphore is very straightforward. Okay. Yeah, semaphore creation. In Xenu, all the semaphores are created at runtime. They are dynamic. And this is how you create a semaphore. It's very simple, right? Because all the, you just modify one of the semaphore entries in the semaphore table and initialize its count, okay? So here, this new sem, this is the allocation for this semaphore instance, but it involves the memory management component in Xenu, so we won't dive into the detail for now. Later, after we learn about memory management, we will be able to understand its implementation details. Okay? Oh, sorry. Let me see. Sorry, I might have spoken too fast. Right? So this seems that in this version of Xenu, all the SAM tables, the items in the SAM table is actually predefined, right? So you have all the semaphores in the SAM table already allocated. This new SAM is just wrapper, and it returns the next available semaphore for you to use. Right? So they are not really allocating these semaphores dynamically in memory, but it's already predefined in an array, and you are just referencing one of them in this new SAM, this function. Okay, yeah, sorry I made a mistake. But I think that there's another thing confused with a stack. Right? So when you create a process, you're gonna call you're gonna allocate a stack, and the allocation of stack uses the low-level memory management of Xenu, which we'll learn later. Right? Here, it just uses a predefined array, so it's very straightforward. Okay. Some subtlety, right? When you delete a semaphore, right? If one or more process may be waiting when the semaphore is deleted, and we must choose how to depose each waiting process. In Xenu, it's very simple. If a process is waiting on semaphore, when the semaphore is deleted, the process becomes ready. So if you delete a semaphore, it means that all of the processes locking on this semaphore, waiting to enter some critical region, can suddenly enter that critical region. It's not protected anymore. Okay. So this in Xenu, this is very simple implementation. Okay. So this is how you delete the semaphore, and so here the deletion, right? So this is where you remove the item from the semaphore list and call ready, so that they will be read ready. Okay. Okay. So here this is a reschedule control. Defer start, defer stop, right? So this is if you're interested, you can read the code. This actually, anyone want to take a guess? What does this mean? And why do we need this reschedule control? I think here. Okay, what is the point of this? Yes.
It keeps rescheduling getting called while you're making all the other processes ready.
Exactly. Right. That's right. So in this while loop, because this is a deletion for a semaphore, we need to release all of the processes that are blocked on this semaphore. Right? So we cannot just remove one of the blocked process and reschedule. We don't want to do that. So we want to remove all of them, right? Make all of them ready before we call reschedule. Right? So this is a reschedule control its purpose. It says that starting from this point, all the later reschedule is going to be delayed. We're not going to do reschedule. And then after we make all the processes ready, then this is a reschedule defer stop, means that, okay, if any reschedule has been delayed, we need to do reschedule here. Okay. All right. Now, let's look at one example. So these slides have been uploaded a while back, so maybe some of you have already looked at this example. Okay, so yeah, let's look at this example and see whether everyone understands how it works. So we have a process, and this process creates one semaphore, and this semaphore is initialized with number 1. So you can, yeah, it's essentially a mutex, a lock, right? And there are 3 processes, ABC, execute the following code. We have call this function convoy and the chart print. We have ABC, 3 processes. One prints A, the other prints B, the next one prints C. And each of them run this while loop, right? So it does some computation, use CPU, and it uses mutex to protect the critical region. And in this critical region, it prints the chart print, A, B, or C. And then after this, it calls signal. Okay, so these 3 processes prints A, B, and C respectively. Now, the question. So we observe this behavior. Why does it happen? That's a question. So the behavior is we have initial output, right? 20 continuous A's, 20 continuous B's, 20 continuous C's, and then it goes back to A, right? 20 continuous A's, and so on. But after some time, the output becomes ABC, ABC, ABC. Okay. How does this happen? Right. So can anyone think about it? Right. 30 seconds, 1 minute. Right. I'll give everyone 1 minute. Right. So how does this happen? If you understand how this happens, you understand how semaphore works inside Linux. This might not always be the case for other OS, but in Xenu it happens like this. Why? 1 minute.
I think I should like a semaphore that doesn't real.
He has a 31.
It's gonna definitely. Hell yeah. And real is like cigarette for eyes. Yeah, true. Here's your phone. Eyes are colors. I had to get a cord and I had to show the person a picture of because my plate lights were out, my license plate lights, so I had to replace them, and then I like changed it to color to like show the person that I replaced them,
Oh,
and then I just never changed it back.
Every time I show someone a photo, they're like, what's wrong with you?
Yeah, yeah.
Maybe it's cringe to do
Any
it.
answers?
I don't get it.
It's good. It's good.
How does it happen?
It's good. The line on it's gotten thinner too. Or not.
First idea I had, or I feel like part of the
White
thought
buds.
process is because would this be because like maybe it's a washroom, it's not like I was gonna say yielding in any way, so it's priority to get back in, or is that separate? So it's like priority falls once and then it gets less time. Or is this separate?
I see, I see. Assume that they have equal priority. They always have equal priority. They still have it. Yes?
There's a chance that, say, process of Prince character A, it's gonna call wait, it's gonna get the semaphore, but then there will be a context switch, so process B would then call wait on the semaphore. And then process C would wait on the semaphore once that, has a context switch. And then when A runs again, as soon as it calls signal, it's going to give it to process B. And then as soon as B calls signal, it's gonna give it to process C, and that'll start happening over and over.
Exactly. Right. So that's correct. And let's go through this example step by step, so that you understand how semaphore executes inside Zing. Right? So in the initial phase, it's very straightforward. Okay. So let's go back to the codes. Okay. In the initial phase, what happens is that process A executes this loop 20 times, right? And while it's outside of this critical region, right? Maybe it's in the first think step, while it's using CPU, its time slice has exhausted. Because its time slice has exhausted, so context switch triggers and switch in process B. Okay, and process B also does the same thing, iterates this loop 20 times, and while it's doing the thinking using CPU, exhausted its time slice, and then context switch happens, process C got switched in, and same thing happens for process C, and then process C finishes, process A gets switched in. Right? And then the interesting scenario happen is that when process A is executing inside this critical region between read and signal, okay, context switch happen, right? Because context switch happened while A is holding this semaphore, so when B gets switched in, B can execute this loop, but it will be blocked. Right? It will be blocked. Right? Blocked waiting for the semaphore. Okay? And then when it's blocked, it will switch itself out, and it will switch in process C. Right? And will also be blocked. Okay? And then process A gets switched back in, it will print print A, and then it will call signal, right? And signal will wake up process B, which is in the semaphore's list, right? And then after it wakes up process B will go into this critical region, print B, and then call signal. And when they call signal, it will wake up process C. Okay.
So when A calls signal, the context switches to B.
Yeah.
Why doesn't it stay until it's time slice?
It called reset. Do you remember whenever you call reset, you are forcefully going to check whether there is some process in the ready list that has the same priority as you. If there is, you do run robin. Right? So that's why even though process B has the same equal priority as A, process B will be switched in at that time. Yes.
Why is the fact that, let's say, B switches in? Okay, no, I think that answers this question.
Right. When B switched in, it will print B and it will call signal.
And then it will switch.
Switch to.
Yeah.
Because C is in the separate list. Previously, in the other case, in the initial phase, because no one is in the semaphore list, right? Because all of them, they are doing context switch when they are not in the critical region. Okay, they do context switch when they are not in the critical region. No one is in that list. Yes.
I'm a little confused by the implementation of semaphore with delete, because how do you know after wait if the semaphore hasn't been deleted or if it has been replaced by it has been deleted and used by another process in between?
Delete.
Right.
So the delete implementation. We can go back to that later. Are you asking how delete interacts with this this problem?
After we call wait, like the two reasons why we might run this process is either wait as like we're back in queue, or in between something has deleted the semaphore. So we don't know whether or not we can actually access it or not. So I'm a little confused about that.
Oh, we explained it, right? Delete in Zeno is extremely simple. It does not. When you delete a semaphore, it means that all the process can violate the critical region. They can just enter the critical region.
So how do we know, like after wait, if we're still accessing the critical region? Like if the after wait, like are we actually accessing the critical region or has it been deleted since?
There's no guarantee, right? That's why I said that Zeno is simple. It does not provide such guarantee. So if you delete a semaphore while some other process is waiting for it, it means that you break the other process assumption on the critical region. Instead they are entering the critical region without a semaphore.
I wanted to ask one more question. If let's say A context switches out, causes B to go your way, and C to also go its way, and then A comes back and then runs into signal, like doesn't that mean that like why is it such that after C, like B is waiting, C is waiting, A hits signal, B runs, B hits signal, C runs. Why is it such that A will not be context switched out during the CPU? Like why does it become ABC, ABC? Why isn't it like ABC, BC or something like that?
Well, because the semaphore queue is first in, first out. Because of semaphore queue is first in, first out, and the ready queue is round robin. Right? These two, because of these two mechanisms, that caused ABC, ABC. That
I'm saying like what if A gets context switched out in the CPU, like while using the CPU, and then when it goes to B now, B becomes first to wait.
then you have BCA, 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 or you have a BAC, BAC, something like that. But if you have a pattern, it will repeat itself. So you could have ABC, but BCA, CAB, but once this pattern starts, it repeats itself. Okay. Yeah, I think these questions are simple to answer. And how long thinking time is for you guys. Why does a convoy start? We already explained it. Will the output switchback give me enough time? If lucky, you might be, but the switchback to the initial initial effect, 28, 28B, 20C, that is not very stable, right? So the system will easily get stuck in this unstable state where get stuck in this state where you print ABC. It's very easy to get stuck in this state. Right? Yeah. So knowing the policies of the implementation of scheduler semaphore making the common behavior obvious, this is another question for you guys to think about. Okay. All right. So this is one more thing to explain. I think you can read the remaining of the slides. They are not that important. But there's one thing I want to mention. Okay, so the semaphore queuing policy, right? And yeah, the semaphore queuing policy. So the queue in semaphore in Vue is implemented very simply using first come first serve, or first in first out. Okay, but you can have other possible policies. You could, similar to the ready queue, you can order the processes blocked on each semaphore using their priorities. Okay, and you can do first in first out, or you can random. Right? You can order them in a random order. Okay. In Xenu, they pick a first in first out. That's easy to reason about. Right? But the goal of this semaphore queue management is fairness, right? So similar to process scheduling, the reason we care about semaphore fairness using semaphore is that when there are multiple processes trying to acquire this semaphore, we want to make sure that no process will stop another, right? So if there's no fairness guarantee, it is possible that for a few processes who are competing for the semaphore very frequently, right, one could prevent the others from using the semaphore. Okay, so the goal is fairness. Which semaphore queuing policy implements the goal the best? You can do random. Complete random, that's fair. Right? First in, first out. Slightly worse, but still good. Right? First in, first out, they depend on, it essentially means that if someone uses semaphore very frequently, they might be able to get ahead of the queue very quickly. Right? Yeah, so the first in, first out is slightly worse, but still relatively fair. The other option is using the priority of the processes, which is more unfair. Right? So the higher the process with higher priority, if it uses the semaphore very frequently, it's possible for it to block, to prevent others. Okay. All right. Yeah. So one interesting phenomenon. So this is the point I want to cover, is that the semaphore policy can interact with the scheduling policy in interesting ways. Right? The scheduling policy is when you do context switch, right, which is the process you're going to switch onto the CPU. How do you manage the ready list of CPU of processes? But the semaphore policy is how do you manage the processes that are blocked on the semaphore queue? Right? One manages ready list, the other manages semaphore list, semaphore queue. Okay. The interaction between them could be very interesting. Right? The first question: should a low priority process be allowed to access a resource if a high priority process is also waiting. Should a low priority process, think about this question, should a low priority process be allowed to access a resource? Because you use semaphore to protect the shared access to some resource. Right? Let's imagine this scenario. You have a shared resource and the multiple processes, like 2 processes for example, are using one semaphore to protect their access to this shared resource. Okay. And suppose we are using first in, first out. Like suppose we are using first in, first out. And somehow the low priority process gets into the semaphore queue earlier than the process with higher priority. Okay. Let's just move on to the answers. Okay. So the two questions, right? One is about whether you allow low priority process to violate the priority. The other is you need to guarantee fairness, right? The low priority process, you don't want it to be blocked forever, right? So the choice is very difficult. Right? Usually there's no single best answer. It's usually a trade-off. Right? So first is fairness is not very easy to define. Right? Based on different metrics, you define different fairness. And scheduling and the coordination using semaphore, they interact in very subtle ways. So the choice may affect other OS policies. So that's why in Linux they pick a first in, first out, which means that for the first question, it's true. Right? It is true that a low priority process, if it gets ahead, right, in the queue, it can block, prevent a high priority process from accessing the shared resource. Right, so for the first question, it is true. Okay. And for the second question, it is not true in Linux, right? So because the semaphore queue is first in, first out, so a low priority process will not be blocked forever because the queue will be drained in first in, first out order. Right? As long as you enter the queue, you will be served. Right? So that's why that's how Linux made the trade-off. For first question, yes. For second question, no. Right? Linux avoids starvation, but Linux Linux prevents starvation. But Linux allows a low priority process to access a resource before a high priority process. Okay. All right. So sometimes that kind of interaction, right, a low priority process somehow has a higher priority when accessing some shared resource. Sometimes it's called a priority inversion, right? But you need to control it in a way that it's temporary. Okay. Right. Yeah. So Linux use first in, first out, or first come, first served. The approach has several advantages. It's very straightforward to implement. It's extremely efficient. It works well for traditional use of semaphores. Guarantees all containing process will obtain access, so no one will be starved. But the downside is that a low priority process can obtain access to a shared resource while the high priority process remains blocked. Right? That's a priority inversion. Okay. So the implementation is very simple. All right. Okay. So that is semaphore. Okay. So we finished talking about semaphore. You can start working on that tree. Right? But next we will talk about interrupts, which will be the basic for you to work on some future labs. Right? But I think probably even in the previous labs you might already learn some of them. We're going to explain how interrupt works in detail. But before we start, anyone has some understand how interrupt works and how interrupt is used and how interrupt is handled or implemented in Zeno? Or a high level understanding, right? So how does the interrupt work? With some example usage, right, if you remember any. What is interrupt? Why do we need it?
Yeah, so you can like this have basically asynchronous execution, like the device can do its thing and then tell the CPU to do something.
Right. Interrupt is an asynchronous mechanism. Callback, right? So if you are writing applications, you might have callbacks all the time, and that is one type of callback. So the hardware devices, they can interrupt the CPU to tell interrupt the currently running process or program on the CPU, and tell the OS you need to do something else. Right, that is interrupt. So remember, in the early lecture we showed how a simple simulator of CPU. The simple simulator of CPU is just a big while loop. Right? In the while loop, in every iteration, you execute one program statement or instruction, and then you check whether there's any interrupt. Those are the two major functionality of CPU in every loop iteration. Execute a command, then check whether there's interrupt. If there's any interrupt, call the interrupt handler to handle the interrupt, and then move on to the next iteration. Right? Try to execute the next program statement. Okay, so that is interrupt, right? Interrupt is a mechanism for the devices to notify the CPU you need to stop the current running process and do this interrupt handler, and then after that you can switch back to what you were doing before. Okay, so how does that work? So this thing that keeps popping up is a new software that Purdue enforces on every device that you purchase, employees purchase in Purdue. So I think they might be tired of the security problems that we have been encountering. So they installed this software that kind of monitors your work device and forces you to do upgrade. Like almost every couple of days, they will remind you need to. There are some software updates, and you need to install them, and you need to restart your computer. It's quite bothering, but everyone has to do it. Anyway, yeah, and I guess right, I think it hooks into the lower level of the OS, right, Mac OS. So they cannot easily get rid of it. All right. Ancient history. Every device has a unique hardware interface, and you have code to communicate with the device that is built into the applications, and an application told the device interrupt was not used. Right? What is the reason? Right? Because in the ancient days, every application is written specifically for that hardware. It knows exactly when to use the hardware device and how to use it. So it will proactively use the device. It does not wait for the device to finish its execution and notify the program. Okay? The disadvantage is that it's very painful to write such hardware-specific programs, and we want the program to use arbitrary devices, and we want to upgrade device without rewriting the application. Okay. So we so we build an abstraction, which is the interrupt-driven device manager. Right? So we have a device manager, part of the OS, and these device manager are interrupt-driven. Right? So the OS presents applications with a uniform interface for all devices. The advantage of interrupts. An interrupt mechanism permits the CPU and I/O devices to operate in parallel. Right? CPU can continue executing the process's program, and the I/O device, they can do I/O on the side. Okay, so that's how you have why you have the DMA, direct memory access functionality inside the computer. Although the details differ, the hardware includes a mechanism that automatically interrupts normal processing and informs the OS when the device completes an operation or needs some attention. Okay. A device manager in the OS manages the resources, hides low-level hardware details, and provides an API that the application use and synchronize processes and I/O. So why is interrupt interesting and also challenging? One of the most intellectual difficult aspects of OS arise from the interaction between processes and devices. Right. So process is OS abstraction, device is a hardware reality. Right. And specifically, the connection between interrupts and the process scheduling. Right. It can be very tricky, because interrupt that occurs in one process can enable another. Right? So the interaction between process scheduling and the interrupt handling is very tricky. Okay. So before we talk about the interrupts, there are some review of I/O using interrupts. Right? So the processor starts a device and enables interrupts and it continues with further computation, right? Because it starts this device because it's going to perform some I/O with the device. So the device will perform the request operation, some I/O, and then after that it will reset the interrupt on the bus, and then the processor, CPU, will check for interrupts after each instruction is executed, and it invokes a interrupt handler function if the interrupt is pending. Okay. And it has a special instruction to return from the interrupt mode and resume normal execution. So this is a overall process, how a interrupt is raised and how it finishes execution. Right. So some key ideas. Right. At any time there is a process that is running, and we think of an interrupt as a function call that occurs between two instructions. So this is exactly what I showed you in the previous simplest CPU simulator. You have a big loop. In every loop iteration, execute one instruction, and then check interrupt, and then call interrupt handler if there is one interrupt. Okay. Processes are OS system abstraction, not part of the hardware, and OS cannot afford to context switch whenever an interrupt occurs. And these are some of the constraints that you want to follow when you design OS. Okay. Right. So the consequence of this is that the currently running process will need to execute the interrupt handler. Right. You don't want to have a dedicated interrupt handler process because you don't want to context switch to handle interrupts every time. right? So you have to let the current running process do the interrupt handling, even if the interrupt handling might be for some different process. Okay. Okay. Right. So historical interrupt software. Right? So there are a separate interrupt function was created for each device. Right? That they are usually called the interrupt handlers. And a very low level code, and the interrupt code must handle many details. They need to save and restore registers, set the interrupt mask, find the interrupting device on the bus, and interact with the device to transfer data, reset the device for next interrupt, and return from the interrupt to normal processing. Part of it is very similar to rescape and context switch. You store the current execution context. The other are specific to interrupt handling for hardware devices. Okay. Vectored interrupts. This is the mechanism that OS uses to store the interrupt handlers. You have a vector of functions, and each function is the handler function for one interrupt. That's called a vectored interrupts or interrupt vector. Right. Each device is then a unique integer known as an interrupt request number, IRQ. And the OS stores an array of pointers in memory called the interrupt vector. Okay. And the device applies its IRQ when interrupt the processor, and the interrupt hardware or software uses IRQ as index into the interrupt vector. Okay, and this array, remember every item in this vector is a pointer. That pointer points to a specified location which has the interrupt handler function. Okay, that's how, given the IRQ, you jump to its corresponding interrupt handler function, because the function pointer is stored in this interrupt vector. Okay, so this is the diagram showing what it looks like, right? So this is the vector, and this is the pointer. Right? It points to the function or the code to handle device zero's interrupts. And this one points to the code that handles device one's interrupts. And when device I interrupts, the process executes code starting at the location interrupt vector I. Okay, so every OS, likely, right? So every OS, they'll follow this structure. Okay. And when you starting up your system, you do this, your OS will do this device interrupt handler registration, which means that it's going to initialize this vector, make sure that they point to the correct interrupt handler functions. Okay. Right, so a more modern interrupt software has an interrupt dispatcher. Right? So you have essentially another layer of abstraction, a dispatcher that checks the IRQ, the interrupt number, and invokes the corresponding interrupt handlers. So it is a single function to all interrupts, handles low-level details such as finding the interrupt device on the bus, set up the environment needed for a function call, and calls a device-specific function. Some functionality may be incorporated into the interrupt controller chip, so which means that it's going to be executed in the hardware. And the interrupt handler only handles the specific operation for each device. It's invoked by the dispatcher, performs all interaction with the specific device. It does not do other things like storing the execution context anymore. The interrupt dispatcher does that. And this is a more modern two-level interrupt software. Right, so it looks like this. The hardware interrupt goes to this dispatcher, and in this dispatcher, it's going to execute some common functionalities to all interrupt handlers, like storing the current execution context, set up the function call stack, and then call the interrupt handler. Yeah, so because of this two-layer design, the interrupt dispatcher is going to take over these functionalities, right? Save execution context and machine state, identify the interrupting device, use the RQ number to find which device is interrupting, and establish the high-level runtime environment needed by the interrupt handler function, and then call a specific device-specific interrupt handler, which is written in C. Okay. Upon returning from the interrupt handler will communicate with the device and restart the next operation on the device, eventually return to the interrupt dispatcher, and the interrupt dispatcher executes a special hardware instruction known as return from interrupt. Okay, so this special hardware instruction will do these two things atomically: resets the function pointer to the saved value, right, so where from its original execution context, and enable interrupts. Right, do these two things atomically. Okay, so this is the ARM exception vectors, but I think that's this is the example of interrupts on the x86 Galileo machine that you guys are using in the lab. So you have hardware interrupts, you have a Ethernet dispatcher, serial dispatcher, and other dispatchers. So you have multiple dispatchers, and each of them has a handler. Okay. So this is a BeagleBone Black, another platform, right? So the structure is slightly different, but the overall idea is still the same. One thing that is different from hardware interrupt is exceptions. So such as divide by zero and page faults. These OS exceptions, they also follow the vector approach similar to hardware interrupt handlers. So the Galileo machine illustrates interrupts and exceptions integrated into single exception vector. And the exception vector is really looks the same as the interrupt vector. Okay. The other backend has a two-level scheme. But these exceptions, you can think of them as software interrupts. They are handled the same way as interrupts. Okay. Let me see. Yeah, I think today let's finish by thinking about this question. I think this question could help give everyone a better understanding of interrupts and how it interacts with processes. Right. So previously, what we explained is very simple, right? So interrupts will be reached by hardware devices, and every hardware device, when it reaches the interrupt, will be handled by some interrupt handler. Right? That's the overall idea. But there are things that are tricky when hardware interrupts and process scheduling interact with each other. And we're going to look at some examples. Right? So first, recall that the hardware disables further interrupts before invoking a dispatcher. Right? So when you have a interrupt that you need to handle, you will disable the other interrupts. Right? And interrupts remain disabled when the dispatcher calls a device-specific interrupt handler. Right? So in this process, during this process, the interrupt handler's execution, interrupts are disabled. Okay. To remain safe, right? A device-specific interrupt handler keep further interrupts disabled until it completes change to global data structures. So one thing that's tricky, what happens if an interrupt calls a function that calls reset and the new process has interrupt enabled? So, yeah, sure, this interrupt handler, when you are executing this interrupt handler, you disabled all interrupts. But somehow in this interrupt handler, you voluntarily call reset yourself. And then you schedule the switch in some other process. And that's bad, because that process, right? That process might have an interrupt enabled, and it could further allow other process to interrupt that process, and you have no control over that. Okay. Right. So this is an example, right? A interrupt handler calls a signal, because signal calls a reset, right? And it is possible reset switches to a new process, and this new process executes with interrupt enabled. Right? It is possible. And when it's executes with interrupt enabled, it is possible another process can switch in. Right? So the best practice is that inside your interrupt handler, try to avoid call any reset. But an interesting question is that, let's say if you allow the process to allow the interrupt handler to call reset and switch in some other process, will this interrupt pile up? Will interrupt pile up indefinitely? Because when you call context switch and another process has the interrupt enabled, it means that another interrupt could happen. So you have nested interrupt handler. Right? You have one interrupt handler executing, and in the middle of it, you switch to another process, and that process has interrupt enabled, and another interrupt happen. Interrupt that process, and you need to execute that interrupt handler. And this goes on. You can have nested interrupt handlers executing, right, in this manner. The question is that will interrupts pile up indefinitely? Right. Think of it's not very difficult question, but thinking about this will help you understand. How process scheduling and interrupt handling, how they interact with each other. Will interrupts pile up indefinitely in this case? Right. The example is here.
Does it have a flag for reader?
Yeah, the context switch, sure. That's a question, right? There's no answer, right? So the context switch will switch in a process and restore the previous interrupt. Restore the previous interrupt set. Right? And then continue execution, it is possible that the process that gets switched in, previously its interrupt flag is enabled, right? Right, so of course in the context switch function itself is disabled, but it will finish executing the context switch and reschedule function and then go back to its normal execution, right? And when it go back to its normal execution, it could have the interrupt enabled. Yes.
Not too sure, but would you be limited by n prop? Like if n prop is 20, there's only so many steps you have. You have to get back to the original function you're calling the scale. If it's a cycle of process 1 calls rescale and process 2, eventually you reach process 20 and process 20 has to go back to process 1 and resolve the other.
Exactly. That's correct. Right. So it's limited by the number of processes that you have. Right? Because remember, every interrupt is handled by the current running process. If a process is running this interrupt handler, it's going to disable interrupts, and even if it calls reschedule, it means that it has its interrupt disabled, and in the future, even if you switch back to this process, it has its interrupt disabled. Right? So eventually, even if this pile up, eventually you will have all the processes in your system enter this disabled mode, interrupt disabled mode. When all of them disable interrupt, then no further interrupts will be able to pile up again. Okay? Right. So we will not pile up indefinitely. So the interrupt status is associated with each process, right? Not with the hardware. After switching to a process that has interrupt enabled, the process can be interrupted. But when it's interrupted, it will disable the interrupts, right? Because the interrupt handler, first step is to disable the interrupts. And in the worst case, all processes will end up executing interrupt code with interrupts disabled. And if another context switch happens, it will be to a process that has the interrupt disabled, and the system must return from an interrupt to have the interrupt enabled again. So the interrupts cannot pile up indefinitely. Okay, so that's it for today. If you have answer questions, come up and write on the case.